Hey everyone, thanks for joining me on this screencast number 6. This one's about slope and rate of change. You remember how this goes? I'm going to present to you a real-world problem, and we're going to solve it using the concepts that we've been learning in class. And this one's about slope and rate of change. We talked oh so long about slope, but rate of change, what is that? It's extremely similar. It's so similar, in fact, it's pretty much the same thing, just with a different name. A rate of change compares a change in one quantity to a change in another quantity. Well, that's kind of exactly what slope is doing. It's calculating a change between two values and a change in another two values, and they're comparing them together. Now, this whole idea of comparing pretty much means that we're dividing them. Yeah, just like with normal slope. Now, do you remember last year when we were talking about ratios, we said that order matters in the sense that what goes in the numerator compared to what goes in the denominator really has a lot of meaning, and how you know what goes in the order or what goes in the numerator or the denominator depends on the actual English that they say. Same thing here. Here's the problem. Okay, internet cafe. Now, for those of you that don't know what an internet cafe is, you get them around the city here and there. But basically, you go there, you pay something per hour, and you get to surf the web. Basically, it's pretty fast Wi-Fi, pretty fast internet, and you go there and you pay. Internet is like $5 an hour, $7 an hour, what have you. Here's a little example of what it was. You don't really see these too often anymore, simply because everyone has a laptop or a tablet, and Wi-Fi that's free is pretty much everywhere, so you don't really have to pay for it anymore. But in the early 2000s, they were everywhere. And when I was abroad, I used these internet cafes so often to communicate back to the United States. But anyways, I digress. Here's the problem. The table shows the cost of using a computer at an internet cafe for a given amount of time. Find the rate of change in cost with respect to time. So we have to find, yes, this rate of change, which, as I have said, is so similar to slope. And we have to find the rate of change in cost with respect to time. So here is the information that we're given. If you spend 2 hours at the internet cafe, you just spent $7. 4 hours, you have to spend $14. 6 hours, and you have to spend $21. Interesting. So basically from there, we have to find the rate of change. Now, what is the rate of change? Well, it's how one quantity compares to a change in another quantity. And those quantities happen to be time and cost. Now, what do they say first? It says find the rate of change in cost with respect to time. That tells us a lot. What did they mention first? They mentioned the change in cost first. And because that was mentioned first, just like with normal ratios, it goes in the numerator because it was mentioned first. And what was mentioned second? With respect to time, well, that means the change in time. So the change in time is, of course, the denominator. So we have to, based on the way they described it, change in cost with respect to time. Heck, they could have said the change in time with respect to cost, but that would have flipped this whole thing around. No. They want it very specific. They want the change in cost with respect to time, which means cost must go in the numerator and time must go in the denominator. All right, good. Now, notice that we don't have variables in this example. Well, that's okay. That doesn't mean that we can't have them. It just means we have to put them in. So let's do that. Let's say the time in hours is X, and the cost in dollars is Y. Based on that, we can now calculate the rate of change. But we got to do some work too. Now, one thing to remember that since we said change in cost is going to be in our numerator, and we said cost is Y, that means all the Y values must go in the numerator. And since we said change in time is our X value, all the X values must go in the denominator, which represents the change in time. So it's going to be technically Y over X, just like the normal slope formula. The changes in Y's divided by the changes in X. All right, so what are our ordered pairs? Let's examine that. To find our ordered pairs, what we can do is simply look at the data that we're given. All right, let's look at that. This time in hours, this cost in dollars. We can create 3 ordered pairs based on this. Remember, we said time is X and cost is y, which means anything in the time row would be our x value, and anything in the cost row would be our y value. So, based on the first one, 2 hours means $7, 2 comma 7. And based on our second one, 4 hours means $14, 4 comma 14. And yep, you guessed it, the last one, 6 hours means $21, 6 comma 21. Because what we're saying here is that every ordered pair, x comma y, well, the x represents the hours, and the y represents the dollars, the money spent. Very good. All right, so now we have our 3 ordered pairs in which we will work with. Now, you might remember from class we said in order to calculate slope, aka rate of change, you need only 2 points, but yet we have 3. That's fine. How do we handle that? Let's find out. Just keep something in mind. You might have more information than needed, and that's exactly what's going on here. We are given far more information than we need. We have 3 ordered pairs, but to calculate slope, rate of change, you only need 2. So one of them we could just really and utterly, completely ignore, and we should, in theory, still get the correct answer. So here we have our 3 points, 2, 7, 4, 14, 6, 21. Now which one's going to be x1, y1, x2, y2? Doesn't really matter. We have free gain to find out which one that is. You know what? Just so we can read from left to right, let's say 2, 7 is x1, y1, and 4, 14 is x2, y2. All right, now we're ready to solve. So let's get rid of y2. Let's replace it with 14. Let's get rid of y1. Let's replace it with 7. Let's get rid of x2. Let's replace that with 4. Let's get rid of x1. And let's replace that with 2. There we go. Nice little animation there. And now we're ready to solve. That's not so bad. 14 minus 7 is 7. 4 minus 2 is 2. So we have 7 over 2. Well, because this is a rate of change, it's a real world problem, we are always welcome to change that into a decimal. And that decimal is 3.5. All right, so we find out our rate of change is 3.5. Now, what does that mean in the context of this problem? That's what we need to also determine, which we'll do in just a moment. But of course, it's important to be thorough. I mean, what if the person sitting next to you or someone else doing this problem said, no, this 2, 7 here, I'm not even going to use that one. I'm going to use 4, 14, and 6, 21. In other words, 4, 14 is x1, y1, and 6, 21 is x2, y2. Will I still get the same rate of change? 3.5? Well, let's find out. y2 now becomes 21. y1 now becomes 14. x2 now becomes 6. x1 now becomes 4. There we go. Now let's calculate. In theory, we should get the same thing. Let's see. 21 minus 14. Oh, that's still 7. And 6 minus, wow, that's still 2. And 7 over 2, yeah, that's still 3.5. So yes, it didn't matter which 2 points we used as long as we're dealing with a linear equation, which we happen to be, the rate of change is going to be the same. And because you know Mr. Ripes likes to drive these points home with great fury, what if a third person said, you know what, I'm going to use 2, 7 as x1, y1. I'm not even going to use this 4, 14. Who cares? I don't need that one. What if I said 6, 21 was x2, y2? Will I still get the same 3.5 rate of change? Observe, ladies and gentlemen. You're probably thinking, yes, Mr. Ripes, I'm going to fast forward through the video. Okay, well, that's your prerogative, but watch. y2 is 21. y1 is 7. x2 6. x1, 2. Wow, check this out. Okay, 21 minus 7. Well, that's 14 this time. And 6 minus 2 is 4. We didn't seem to get the same 7 over 2. Or did we? 14 over 4 we know does reduce to 7 halves, which of course is the same 3.5. Now, did we have to solve it 3 different ways, 3 different times, using different ordered pairs every single time? No, we did not have to. We were just thorough in checking our work, and as you can see, every single time we did it, we got 3.5. But of course, those three options weren't our only options. What if somebody said that this point is x1, y1, and this point is x2, y2? Will we still get the same thing? Well, I've already plugged in the values here, so let's see here. 7 minus 14 is negative 7, 2 minus 4 is negative 2, and look at that. Negative 7 divided by negative 2 is, yes, positive 3.5, so there it is again. But we're not through, folks. What if somebody said, okay, 14 minus 21 over 4 minus 6? Will they still get the same thing? 14 minus 21 is negative 7. 4 minus 6 is negative 2. And look, we still get 3.5. That is positive. Last one, folks, I promise. So what if somebody were to say, okay, the numerator is now 7 minus 21, and the denominator is 2 minus 6. Will we still get the same thing? 7 minus 21, negative 14. 2 minus 6, negative 4. Ah, but wait a minute. Negative 14 divided by negative 4, that does reduce to positive 7 over 2, which, of course, is 3.5. So no matter what, we got 3.5 as our rate of change. Okay, now what the heck does that mean? All right, so let's see how this does relate to this problem, this real-world internet cafe problem. 3.5, what does that mean? Well, remember what we said at the beginning of this screencast. We said that the rate of change is the change in cost with respect to time. In other words, the change in cost over the change in time, which means we want to state our rate of change as a fraction. So we need to take this 3.5 and let's change that to a fraction. Well, that's easy to do. That's 3.5 over 1. Well, all right then. Now, well, we see that 3.5 is in the numerator and 1 is in the denominator. So let's compare that to our change in cost over change in time. Let's see. Let's take 3.5. We know that's in the numerator, so let's put that up there. And we know that that over 1 is the denominator, so let's put that down there. Let's set them equal to each other, and we can clearly see that the change in cost is 3.5 and the change in time is 1. But still, what the heck does any of that mean? You know what? It's change in cost, which is 3.5. It's cost, which means 3.5 is $3.50. And the change in time, well, what was the time measured in? Well, according to this, time was in hours, so that 1 represents 1 hour. We've got it, folks. Our rate of change is $3.50 for every 1 hour. In other words, if you go to this internet cafe, for every 1 hour you spend there, you're spending $3.50, which is pretty cheap, actually. And we can even have seen that right from the start. Look, if it's 2 hours and costs $7, well, then clearly 1 hour is $3.50. So we could have seen it that way as well. But nice job. We just calculated the rate of change, and we did it multiple ways. How many ways do you need to do it? Of course, only one. Mr. Ripes, why'd you just waste all my time doing it so many different ways? To show you that you have variety, because variety is the spice of life. Always keep that in mind, folks. And as I've always said, there's always more than one way to solve any math problem. Heck, here we just did 6. Nice job. All right, time for your problem, for you to solve and explain. Here it is, folks. This one is about exercise. Here we go, exercise. The table shows the distance a person walks for exercise. Walking is great exercise. If ever you're in a bad mood, take a nice little walk. It's the best way to get better. Trust me. Find the rate of change in distance with respect to time. So we have to find a rate of change again, which is essentially nothing more than slope, but it's in distance with respect to time. And time is in 30, 60, and 90 minutes, and distance is in 1.5, 3, and 4.5 miles. Now we see that the distance formula, of course, is here. Again, let me give you a little helping hand. Based on the fact that the rate of change in distance with respect to time, notice that distance is mentioned first, then time, which means in the numerator, we have to calculate the change in, that's right, you said it, distance first. And in the denominator, because time was mentioned second, the change in time. And to help yourself out, give time and distance, minutes and miles, they're each own variable. Let's let time be x and distance be y. Then, as you can clearly see, you can take these data points and make them into ordered pairs. Here, I'll do the first one for you. If the time is 30 minutes and you've gone 1.5 miles, that would represent 30, 1.5. And of course, you can fill in the rest here and here based on that. And I want you to calculate the rate of change in distance with respect to time. Notice that in the previous answer I just gave, I didn't just say 3.5. No, 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 no. This is a real world problem, and you have to have your units. I said 3.5 represents $3.50 for every 1 hour. Well, I want you to also give me your final answer with its proper units in the numerator and its proper units in the denominator. Notice that distance right here is your y values, and since the numerator is the change in distance, y is going to be in the numerator again, so your numerator, its unit will be miles. And because of that, the change in time, which is in the denominator here, and that's your x value, okay, so that's going to be x. So it's going to be miles over minutes. What is the specific number that represents the rate of change in miles per minute? That is what you need to tell me. Show all your work, and please do explain. Again, you do not have to calculate it all those different times. You can if you want to, but only once, of course, is enough. Good luck, everyone. Let me know if you have any questions.